Greetings again. This is our week 3 video class, and I'm going to talk about two new von Neumann architectures today. And these are Vesp 2.0 and CodeMill. Vesp 2.0 is an extension of Vesp 1.0 architecture, and it includes a new register, which we call IX, and 8 new instructions, which are described in this table here. These are increment, decrement, and or shift left, shift right, move with an index, and move with an index instruction. The first one moves with the index register from an array of locations, and second one moves also with the index register to an array of locations. So one is from, one is to. Let us actually look at these instructions a little bit. So increment and decrement instructions are useful for index manipulations. You could actually have a second array, for example, and your IX would be able to help you with one of those two arrays, and then you have to use another location in memory for indexing, and that would then these would come in handy. Instead of like using an add instruction, you could actually use these. Because add would have to involve the B register itself. And or instructions, or IOR instructions, are useful for bit processing and masking when you're doing logic decisions or logical expressions. Then you could actually use these instructions. Shift left and shift right instructions are useful for integer multiplication and division, if nothing else. Of course, they are useful in their own right for, again, bit processing. But if you use them only for multiplication and division, then shifting left multiplies a number by 2, and shifting right divides it by 2. So this example illustrates that. 12 becomes 24 when you shift it left, and it becomes 6 when you shift it right. You have to be careful when you shift things right. If the number is odd, then you're going to lose that rightmost bit. For example, if you shift 13 by 1 bit to the right, then you get actually 6. There's no 6.5 when you think about numbers as integers. Now, let's talk a little bit more about these two move instructions. Here's the move from or move with an index register from an array of locations instruction, which is MXF basically. So MXF instruction uses IX in this case as the source of the operand. So whatever IX is points to the place where the operand that we want to move is found. That operand is then moved to the location in memory whose address is given in the address portion of our so-called MXF instruction. So there's really no second 16-bit word here, as in the case of, for example, move instruction in Vesp 1.0. We don't require that. We actually hold one of that particular 16-bit information, in this case, in our IX register. And the direction of the move is from where IX points towards where the instruction's address field points to. IX gets incremented after this operation. So that's MXF, and the MXT is just the opposite direction-wise. So IX actually points to the place where the operand is going to move to, and the address portion of MXT it points to the location where the operand is found. Again, the value of IX is incremented after the operation instruction is executed, that is. Now let's go on to CodeMill. CodeMill is a graphics-based complex instruction set architecture computer. And it is really a von Neumann architecture still. It's a serial machine. But its instruction set is a lot larger than, contains a lot more instructions than Vesp 1.0 and Vesp 2.0. It uses 1 and 2 address instruction formats. It supports immediate, direct, indirect, relative, indexed, auto-increment, and decrement addressing mechanisms for memory access. It has a built-in stack and supports stack operations. It includes a pair of instructions that are to make calls and returns from a subroutine. They would be basically JSR and RTS instructions, as we will see them later in the next, I think, lecture, a video lecture. And CodeMill also provides input-output processing by a pair of instructions that are actually called send and receive. And it's implemented in C as a simulator, so you can actually execute and or step through assembly language programs and view the operations of a computer within its control registers like program counter, IR, stack pointer, etc. Its scratchpad you can also view, and you can actually look at its random access memory, RAM, frame buffer, video RAM, VRAM, stack, as well as its graphics port, that is its screen. So here are these some of these instructions, probably most of them here. So these are load instructions: immediate load, direct load, indirect load, relative load, index load, register load, auto increment load, auto decrement load, and store instructions the same way: SDI, STD, STT. So basically immediate, direct, indirect, relative, indexed, register, auto increment, auto decrement. And then you have register, move, and clear instructions. And these are basically move, negative move, absolute move, increment and move, exchange, clear X, and clear a particular register. And register bit level arithmetic and logic instructions you have increment, decrement, negate, complement, swap, halves, shuffle, reverse, inclusive OR, and exclusive OR, NOR, NAND, and exclusive NOR. These are all logic and some arithmetic instructions. And then you have register fixed and floating point arithmetic instructions such as add with carry, subtract with carry, decimal add, decimal subtract, multiply, divide, binary to decimal, decimal to binary, floating point add, floating point subtract, floating point multiply, floating point divide. And then you have shift and rotate instructions such as shift right with carry, shift left with carry, rotate right with carry, and rotate left with carry. And then you have instructions that really handle graphics. These are the most maybe significantly different types of things that you would do on a typical von Neumann architectures. And in fact, Intel chips, for example, don't have these direct graphics instructions. Clear frame, set frame, move frame, copy frame, swap frame, flip frame, rotate frame, scale frame, character frame, load frame, and save frame. And you have stack instructions that deal with stack operations. We're going to see examples of this on our next week's video. Load stack pointer, save stack pointers. These take an address or an operand if you like. Clear stack, negate stack, complement stack, duplicate stack, shift left stack, shift right stack, add stack, subtract stack, or stack, end stack, exchange stack. These do not take any operands. Push and pop, they take address. Each of them takes an address. And then control instructions: jump, conditional relative, conditional direct, conditional indirect, and conditional index, jump to subroutine, return from subroutine, no op, set condition codes, and halt. Input and output, send and receive, are two input-output instructions. They take operands to store values as well as identify devices where this send and receive instructions would interact. And so here are some examples: load I R1 comma 4 simply loads a value into a register. This is because it's an I that is immediate, and a direct load, LDD, would take the operand in location 4 and put it into R2. An indirect load would actually go to location 4 to fetch an address, which will then be used to fetch an operand, and then that will be moved into R0. If it's all LDG, that is a registered load, then R1 will actually hold the address to the operand that will be moved into R0. If it's LD plus, then it's an auto increment load. R1 is the register that's actually used that holds the address to the operand that goes into R0, but then the value of R1 is incremented by 1 to point to the next location. That's auto increment. STI 3, 10 is like LDI, except 3 is the location into which 10 is stored. STDR1, 10 is like direct store. That means we actually use R10 as a location, as an address to the location that we store the operand in R1, into which we store the value in R1. And SDT is the instruction that actually uses 10 as the address of the address into which the operand in R7 is stored. And SDG uses, it's similar to LDG, R1 as an address pointer, and then R0 as the place where the operand is held. And SD minus is slightly different than LD plus in terms of the role of R1. When it is minus sign here, we actually use R1 as before, but we decrement it first and then use it as an address to store the operand in R0. Now this could also be used with LD. We could have LD minus. In this case, we're actually loading after we decrement the index register, or the R1 here in this case, by 1 before we do the actual load. So the minus sign means decrement the register that is used as an address first, and then either load or store. Plus means that it's LD plus or ST plus. Do this incrementation after the move, either direction. So jumps and conditional jumps are like direct jumps would be jump D, jump T, jump R, and jump X. These are basically direct, indirect, relative, and index jumps. All that means is that we actually use the address either directly or indirectly or relatively, or as a sort of like a relative value to an index registered in this case. Now we assume that the programs where these jump instructions can be placed always begin at memory location 0. That is, they're loaded into memory location 0. So when we make a jump to location 10, this is just like we move 10 locations down from where we are to jump to that place. If this is an instruction that is located in, for example, someplace, or it doesn't matter in this case, wherever location 10 is in our instruction, in our program, CodeMill program, is where we move. These are a little more involved and really don't get to use them much, so I'm going to skip their description, but you can experiment with them to see what happens. The relative jumps, the conditional jumps rather, have a condition associated with them. So here's a condition that says if R0 is less than or equal to 20. You could say less than, you could say greater than, you could say equal, not equal, you can say those things. You can actually compare them that way. And these could also be two registers compared. And so the idea is that if the condition comes true, then you make a jump. And this is the kind of instruction that you'll use most of the time, where loop would be a label that is attached to an instruction, and you would be jumping to that loop if the condition comes true. relative jump and in a sort of like a, or this could have been actually an indirect jump or a relative jump in this example, would use loop as a displacement. This is also true for this, but the condition has changed from this to this. So again, relative jump would be useful when in fact you want to contain programs within a small space of memory, and you want to give a small field to this address field in an instruction format to keep things short. All right, so these are the examples of jumps and conditional jumps, and here are some two sample programs I've written. Here's one that actually adds an array of operands stored in locations 300 to 399. And these numbers are really not initialized in this case. But all we do is we check to see if we had reached the end of the array. If not, we stay within the loop, and then we use an LD plus instruction to actually use R0 as an index pointer to move the next operand into R2. And then we cleared R1, that's our location into which we accumulate the array of values by adding them together. And then so we do the addition and we jump back to the loop. I've actually written a code that does this before I put it here. Let's see if I can just quickly jump to that. It was here just moments ago. Right, it is. Here it is. So you can see that when I execute this program, just from beginning to end, R0 becomes 400 and R2 becomes 0. So it seems like we got nothing in these locations. That is, they're all 0, but the R0 has become 400. Let's go ahead and take a look at RAM. Now, if you look at RAM, you could see that we've gone too far up here. So let's see, 300 would be basically 256 plus 44. So that's actually a little bit like 44 would be 2C, I guess. So it'd be like 1, 2C is where we want to be at. Let's see, we can go there quickly. So 1, 2C. Right there, I think it is, yeah, so this is basically 32 plus 12 is 44 plus 256. Everything from here down is 0 all the way to, I guess, 399, which will be 256 plus 144. That is actually let's see, 70 is 128. So 744 would be 127, basically F somewhere in there. So we go down all the way down to everything is 0, and that means that the sum should have come out to be 0, which it did. So our program worked just fine, and that's just an illustration of how you set up these loops. So let's go back to our PowerPoint presentation. And the second example does the same thing, except it actually squares the values. Since in this case everything is 0, the result will come out to be the same. So the same program, except we just added a multiply instruction to square things. So we basically talked about Vesp 2.0 instructions, and then described the CodeMill instruction set architecture, and then illustrated its various instructions. Provided also a couple of assembly language programs in Vesp 2.0. So here's homework number 3. Write a Vesp 2.0 machine program to find the largest number in an array of 100 elements stored in locations 0, 64 hexadecimal to 0, C7. Your program must make use of the MXF instruction. to index to an array of locations, which happens to be this array here. And so, you just have to make use of the MXF instruction to really avoid using self-modifying code. Second problem asks the same, I guess, the same programming exercise, but you want to do this in CodeMill. And in the third problem, you're basically required to plot the values of the sum of I numbers versus I 1 through 10 on CodeMill screen. And it says the highest value must be closest to the top of the screen. So what you have here is basically something like this is what I want you to do. This is the screen of CodeMill, and these are the numbers, the sum of I, where I runs from 1 to 10. So this actually concludes our video for the third week. Until next time, take care, and I'll see you all in class on Monday.